Let's talk about the Bolzano-Weierstrass theorem, which is one of the coolest theorems in real analysis. By the way, this is part 17 in a series we're doing on TikTok. So earlier in this series, we talked about why every series, if it converges, must actually be bounded. Now, the converse of that is not true. Like the sequence that oscillates between 0 and 1 is never going to converge to anything. However, every sequence that is bounded does have a convergent subsequence. And this is exactly what the Bolzano-Weierstrass theorem tells us. It says that if we have a sequence that's bounded, then if we select some of the terms, infinitely many, in the same order, then that smaller sequence is going to converge to some limit. There are several proofs of this. In fact, two proofs are so good I couldn't pass up showing both of them to my students. But let's just do one today in this TikTok. Okay, we've got a sequence. We don't know anything about it, but we know that it's bounded. And in fact, we're actually going to forget that for a while and just imagine we know nothing about it. And so if we plotted some of the terms, like maybe the first term is positive, maybe the second term is negative, maybe the third term is way up here. Well, if we did this for all the terms, what could happen, what could be true, is that some of those terms are going to be called peaks, meaning that they're greater than or equal to everything that comes after it in the sequence. So each term of the sequence either is a peak or it's not. For instance, in this example here, I'm trying to illustrate that the third term of the sequence is greater than or equal to everything after it. Maybe so is the fourth term, and so is this later term over here. And maybe I don't know what happens after that. So now let's just admit to ourselves that there are two cases. The first case, we have infinitely many peaks. And the second case, that doesn't happen. We don't have infinitely many peaks. So if we have infinitely many peaks, they actually form a decreasing sequence. Here it's important that sequences need to be infinite. And the first peak is greater than or equal to the second peak, which is greater than or equal to the third peak, and this goes on forever. We've just identified a decreasing sequence. And remember, our whole sequence was bounded, and so we have a decreasing bounded subsequence. Therefore, it converges by the monotone convergence theorem. That's pretty cool. Okay, but what if that doesn't happen? What if we don't have infinitely many peaks? What if we have only a finite number? Like, what if this one up here is our last possible peak? Well, I'm going to show you how to build an increasing subsequence using this fact. And so let's look at this point over here. Take the term of your sequence right after the last peak. Remember, if we have only finitely many peaks, we can take the last one. And so now we're going to start with the term after it. Now that's not a peak. So it has to be strictly less than something that occurs after that. And that's also not a peak. Remember, we've gone past the last one. So that has to be strictly less than something that comes after that. And that's not a peak either. So that has to be strictly less than something later than that. If we continue in this fashion, we can go on forever. We have an infinite sequence, this time an increasing sequence. And so in either case, we've identified a monotone subsequence, and by the monotone convergence theorem, since our original sequence was bounded, this must mean that our subsequence converges. This was a little bit technical. Thanks for sticking with it to the end. On the next video, I'm going to talk about how to use this fact to show our big goal that Cauchy sequences actually converge.